Imagine the first 100 colonists landing on the barren surface of Mars. Millions of miles from Earth, they are completely isolated, living inside a fragile, glowing bubble against the cold vacuum. Sending continuous resupply rockets across that distance is mathematically and financially impossible. The payload costs are simply too high to sustain a dependent population. To survive the long term, these settlers have to bring their own self-sustaining biosphere. They are essentially building a modern space ark. Colonizing a dead planet couples structural engineering with the task of constructing an entire biological food web from scratch. Every single gram of mass and cubic centimeter of volume placed on a rocket requires an exorbitant amount of fuel to escape Earth's gravity. That harsh gravitational math instantly disqualifies traditional land-intensive agriculture. Cows, for example, consume massive amounts of water and grain, require huge spatial footprints, and produce toxic methane gas. They are far too heavy and resource-intensive to leave the launch pad. A new rule governs the space ark. An animal only secures a ticket if it provides absolute, ruthless biological efficiency. This hub-and-spoke layout illustrates how these creatures will actually live, housed within interconnected, highly confined dome habitats. The first candidate to make the cut is the chicken. They act as continuous protein converters, yielding a steady supply of calories through egg production without requiring immediate slaughter. They also possess a major logistical advantage during early transit. Instead of transporting fragile live adults, thousands of chickens can be shipped highly efficiently as lightweight, fertilized eggs. The second candidate is the rabbit. Their rapid reproduction cycles and minimal space requirements make them highly effective for dense meat production. The third candidate is the goat. Roughly human-sized, they act as the ideal biorefinery mammals for an off-world settlement. Goats serve a specific utility in the colony's loop. They digest the tough, inedible cellulose left over from hydroponic plant waste and convert it directly into high-calorie milk. Together, these three species represent the peak of macroscopic efficiency. They form the visible machinery of an off-world food web. Yet that entire visible machinery will rapidly collapse without a microscopic foundation to securely recycle their waste. This flowchart shows a bioregenerative life support system, or BLiSS. To keep the colony alive, human, animal, and plant compartments must connect in a continuous loop. Fungi and microbes act as the ultimate recyclers, breaking down toxic biological waste into fertilizers and biogas. This cross-section illustration highlights aquaponics, the most mature example of this integration. The biological transaction is precise. Fish waste feeds a layer of nitrifying bacteria. Those bacteria process the waste into nitrates, which then feed the plant roots suspended above. The perfect space farm is a meticulously balanced, closed-loop biological machine. Space bioethicists are raising a major concern regarding this mechanical approach. They point to the sharp divide between biological survival and psychological welfare. According to welfarist ethical principles, keeping an animal alive is morally irrelevant if that creature lacks the capacity to lead a good life. The physical environment alone inflicts a heavy toll. Living in 1/3 Martian gravity alters natural bone and muscle development in livestock, leading to lifelong physical stress. Then there is the psychological burden. These animals face multi-generational confinement inside cramped, windowless, artificial habitats with zero exposure to natural ecosystems. The exact biological traits that make these species highly efficient for the space ark also make them uniquely vulnerable to suffering inside it. The strict logistical requirements of space colonization, optimizing entirely for efficiency under extreme resource scarcity, match the exact economic logic that birthed Earth's factory farms. This is what maximum efficiency looks like for a high-value protein converter. Thousands of birds stacked in tightly controlled, unnatural conditions to maximize yield. That same ruthless spatial efficiency translates directly to intelligent mammals, confining them to high-density, bare metal pens. In our quest to survive on new worlds, we're on the verge of exporting concentrated animal feeding operations to the stars. Maintaining biological life in a tin can is a technical achievement, but it leaves the moral question of whether we should do it at all. If you were building the mission to Mars, Which animals would you include on the manifest, and how would you ensure their protection? Let us know in the comments.